Welcome back. In this next lesson, I want to take a look at Venn diagrams, which are a geometric technique that will let us consider unions and intersections of more complicated events than what we were able to do using the techniques from the previous lesson. I'm going to begin by reviewing a couple of key ideas from last time, then briefly mention what Venn diagrams are, but I'm mostly going to be covering this idea by example. So I'll look at a couple of old exam problems, then address some more complicated cases that could lead to some more complicated problems. And so first, what did we do last time? We began with talking about a sample space S. In the probability of the sample space, we're guaranteed an event that the sample space would occur, so probability of the sample space is 1. The empty set will never occur, so probability of the empty set is 0. And we said that the probability of A union B is the probability of A plus the probability of B minus a correction factor from double counting the intersection, so minus the probability of the intersection. Actually, before we looked at that, we looked at the special case in which A1 intersect A2 is the empty set. So the probability of A1 intersect A2 was 0, and we just said the probability of the union was the probability of one plus the probability of the other. Now, we could generalize this second version to say that if I have a bunch of things with empty intersections, right? So if AI intersect AJ is the empty set for all I not equal to J, if you prefer, if all of my AIs and AJs are mutually exclusive, then the probability of the union is the sum of the probabilities. In general, the probability of the union is less than or equal to the sum of the probabilities because you have to make little adjustments like this. And we'll talk about that more in the upcoming lesson. We also talked about complements. We said that A intersect A prime if that was the empty set. Sorry, we said A and A prime are complements means their intersection is the empty set, their union is a whole space. And so 1 is the probability of the whole space, is the sum of their probabilities. There's no intersection to adjust for because the probability of the intersection is empty. And you can solve for 1 in terms of the other. You get the probability of A is 1 minus the probability of A prime, and vice versa. The probability of A prime is 1 minus the probability of A. Now the point of Venn diagrams is that what if we have more than 2 events that are not disjoint? How can we proceed then? Well, that's what Venn diagrams are for. They're a visual way that let us represent unions and intersections, and as a result, they'll let us deal with more complicated cases than what we have seen so far. Here's a variation on an old exam problem to start with. If you've already seen Venn diagrams, you should pause now. But if you haven't quite seen them yet, let me just show you the basic visual setup, and then you can pause and try to get the rest of it. I have 3 different types of viewers I care about: those who watch gymnastics, those who watch baseball, and those who watch soccer. So I have a state space. It's going to consist of everybody who could potentially, everybody who's in this group that's being surveyed. Some of these people, which I'll denote with a green rounded rectangle labeled G, watch gymnastics. The traditional way of drawing Venn diagrams is to draw circles. I prefer to draw rectangles for a reason that I'll explain in just a minute involving the triple intersection. It makes things a little easier to write with. I would in fact actually draw strict rectangles, except for the fact that everybody else in the whole wide world draws these circles, and so I make them sort of more rounded rectangles just as a slight acknowledgement of what the general custom is. But I'll get to in just a second why I like the rectangles. So now let my rectangle G be gymnastics. Likewise, I have a rectangle for those who watch baseball and those who watch soccer. Now, the reason why I'm drawing these as these rectangles is now the intersection of all 3 of these is this nice big rectangular area that I can write in. If I'm writing them as little circles, then the triple intersection is almost invariably too small to write in legibly. All right, now, what are we going to do here with a Venn diagram? Well, I have all this different information. I want to try to label my picture. And what I'm going to do is I'm going to begin with the innermost statement saying that 5% watch all 3 of these sports, and I'm going to try to work my way out. So I like to begin this very middle. 5% watch all 3 sports. I want to be in the green rectangle. I want to be in the blue rectangle. Blue and green is this intersection right here. I also want to watch soccer. I want to be in this lower rectangle, so meaning I'm just in this region right there. That's my triple intersection, and that's probably 5%. If you haven't done so yet, this would be a great place to pause, see if you can figure out how the rest of the diagram can get labeled. I am slowly going to work my way out. What's the next way we can work our way out? 11% watch gymnastics and baseball. The people watching gymnastics and baseball, that's this G and B intersection. 11% are in both halves of that rectangle. 5% are in the bottom half. It adds up to 11%, so it has to be 11% minus 5%, or 6% has to be in this top highlighted bit. 8% watch baseball and soccer. Well, that's this 5% plus this extra little corner. These have to add up to 8%, so I have to have 3% in the baseball and soccer only with no gymnastics. 9% watch gymnastics and soccer. That's these two pieces. I know about 0.05, so I have to have 0.04 left. All right, now I'm slowly working my way up. 21% watch soccer. I know about 0.04, 0.05, and 0.03. So what's left down here, that adds up 0.04 plus 0.05 plus 0.03 is 0.12. So what's left must be 21% minus the 12% that I know about, or 9% left over. Likewise, you could use a 31% watch gymnastics to say, okay, everything in the G rectangle adds up to 31. So I have 0.16 in this top left, the gymnastics only piece. 25% watch baseball, so I have 11% in the baseball only piece. I want people who watch none of the three sports. Since you watch none of the sports means you're outside of everything that I've labeled. Everything in the state space has to add up to 1. I just have a complement here, so I just do 1 minus everything else. So 1 minus the 0.16, minus the 0.06, minus the 0.11, and so on, going through down all the pieces. So I get 1 minus 0.54, or a final answer of 0.46. Here's a somewhat trickier example for you to pause and try to work. Here we again have 3 types, A, B, and C. People may choose either no supplement coverages. They may choose either exactly 2 or none. So you can't choose an odd number. So what does that mean for my Venn diagram? Well, again, I make my big rectangle for a state space with 3 smaller rounded rectangles A, B, and C inside. You may choose either exactly 2 or 0. So you cannot choose all 3. And you cannot choose A only, or B only, or C only. What about A and B? Do we know how many choose that? Well, I know that a quarter choose A. That's not the same thing as saying a quarter choose A and B. It just says a quarter choose A. Well, what I can do when I have a little bit that I don't know is I can just put a random variable, not a random variable, a variable X for saying I have A and B. It's one of the missing pieces, A and B. It's somewhat arbitrary as to which of the pieces I want to fill in with my variable X, but here I'm just going to call it A intersect B. What's left in A has to add up to a quarter. I know about 0, I know about 0, I know about X, so what's left is a quarter minus X. So I've used up this 1/4. Next up, 1/3 use B. I want to use up this 1/3. I know that about 0, 0, and X in B. What's left here must be 1/3 minus X. All right, so that's my initial picture. How can I take advantage of it? I don't know X yet. What else have I not done? I've used the 1/4. I've used the 1/3. I haven't yet used my 5/12. On exam problems, they tend not to give you extra information. You tend to have to use all the pieces of information you give them. So I have to find a way to use this 5/12. How can I use that 5/12? Well, I know the probability C is 5/12. So what's the chance of C? It's 0 plus 0 plus a quarter minus X plus a third minus X. So 5/12, the chance of C is a quarter minus X plus a third minus X, which adds up to 7/12 minus 2X. And I can solve and get the X is equal to 1/12. I want the probability of none of these coverages. I want the probability of the complement of A union B union C. So that's 1 minus everything I know about. It's 1 minus X minus 1/4 minus X minus 1/3 minus X. And you just plug in X is 1/12 into all those things and you get 1/2 out as the answer. Now, for this particular problem, there happened to have been an alternate solution. One of the things that makes probability both fun and challenging at the same time is that there are often multiple ways of doing a problem. So here I want to show you a second approach. This second approach happens not to generalize very well to other problems. So the first approach is more important to understand than the second one. But the second one I think is cute enough to be worth taking a look at. What is the probability of A plus probability of B plus probability of C? Because each person either buys 0 coverages or 2 coverages, if I sum up my probabilities, that will count each person who buys coverage twice. Because if I bought A and B, I'm counted in the probability of A and the probability of B. If I bought A and C, I'm counted in the probability of A and the probability of C. If I bought B and C, I'm counted in the probability of B plus probability of C. So this counts each person who buys coverage exactly twice. What about the probability of A union B union C? That's everybody who buys coverage. But since everybody who buys coverage buys 2 coverages, this is counting everybody once, and this is counting everybody twice. So the sum of my probabilities is twice the probability of the union. My probabilities, I all know, I can just plug them all in. And so I get that the sum of these probabilities is twice the probability of the union. So 1/2 is the probability of the union. I want the probability of the complement, so I want 1 minus that 1/2. So again, I get 1/2 doing it this way. Right? Now let's go back, take a step back and look at some general theory. We say that two events A and B are mutually exclusive, or sometimes we'll call them mutually disjoint. These mean the exact same thing. If the event A intersect B, which we'll often abbreviate as just AB, we'll just sort of suppress the intersection sign, is equal to the empty set. All right, so what that means is that the probability of A intersect B is equal to the probability of AB. As I said, just in my other way of writing it, that probability is equal to 0 because the probability of the empty set is 0. If I'm talking about it in terms of a Venn diagram, I can just draw these things as being non-overlapping sets. All right, so I have some set A, I have some other non-overlapping set B. If I have 4 or more events, typically some of them will be mutually exclusive in order to simplify any Venn diagrams that you need to draw. So if they give you this on an exam where you have 4 or more events, I've never heard of more than 4 showing up in an exam, but if you have 4 events in an exam problem, you want to first look at which ones are mutually exclusive to sort of simplify your picture a little bit. And so here's an example of how we can use being mutually exclusive to simplify our picture. This is another great place to pause and work the problem, keeping in mind what we just talked about. We just looked at being mutually exclusive, and so that's the first hint of what you want to use here. And so now I have 4 events. Those who watch Fox, people who watch CNN, people who watch MSNBC, and people who watch The Daily Show. I count up to 4 things and say, okay, I'm going to draw a Venn diagram. And I'm also really going to hope that I have some ways to simplify it, that I have some things that are mutually exclusive. Nobody watches Fox and MSNBC. All right, what does that tell me? That tells me that I can have non-overlapping rectangles for the people watching Fox, which I'm labeling with an F, and those watching MSNBC, who I'm labeling with an M. Also, we're told that no one watches CNN and The Daily Show. So my Daily Show rectangle and my CNN rectangle are going to be disjoint and, again, not overlap at all. All right, so that's my initial setup of my picture, which is much simpler than the potential intersections I could have gotten with 4 things. Now I want to try to start in some relative insides and work my way out. 13% watch only CNN. Well, only CNN means just this tiny little piece here that's in my CNN rectangle, but neither the Fox nor the MSNBC rectangle. So that's 0.13 watch only CNN. 26% get their news only from The Daily Show. And nobody's foolish enough to watch only MSNBC. A total of 10% of the people watch MSNBC. So I know about the 0 here. I have 2 other parts. The people who watch MSNBC and The Daily Show, and the people who watch MSNBC and CNN. I'm going to let X be those who watch MSNBC and The Daily Show. What's left over? This adds up to 10%. I know about 0, I know about X, so what's left over is 0.1 minus X. 29% watch The Daily Show. I know about 0.26, I know about X, so what's left is 0.29 minus 0.26 minus X, and 0.29 minus 0.26 is 0.03, so I have 0.03 minus X. 25% watch CNN. I know about 0.13 plus 0.1 or 0.23 minus X. So 0.25 minus 0.23 minus X is 0.02 plus X. The minus sign gets canceled. And finally, 30% watch Fox News. I know about the 2 pieces on the outside. Those add up to 0.05. So I'm left with 0.25 watching Fox News only. I want the probability of the people who watch none of the 4. So that's our picture. How do we use our picture? To watch none of the 4, I just want to do 1 minus all these pieces that I have. Perhaps I want to solve for X first, although it turns out to not be possible. I don't have enough information to solve for X. That turns out not to matter, though. Because here, look at this coolness that happens. I just do 1 minus all these pieces. So 1 minus 0.03 minus X, plus 0.25, plus 0.02 plus X, minus 0.26, minus 0.13, minus X, minus, this 0.1 minus X. This first bit that I actually put in parentheses, that was the chance of watching Fox News. That was just 0.3. The 0.26 and the 0.13 remain what they were. This last piece I had in the last parentheses ends up being 0.1. Essentially I'm just canceling out my X's. And I get a final answer of 0.21.